Right? So we have discussed the terms related to your traveling wave, that is your voltage and current wave. Those are propagation constant, which is sum of a real term and imaginary term. The real term is known as attenuation constant, where just the magnitude is being varying. And the imaginary term beta is termed as phase constant, where magnitude remains constant, the phase angle varies. Right? The next concept was characteristics impedance. So in characteristic impedance, as I said, the characteristics of line is defined by the parameters, line constants R, L, C, and G. Right? So how they are behaving when a voltage or current wave is traveling the line, how these parameters are behaving as determined by your characteristics impedance. Right? So this characteristic impedance, again, we have defined it as square root of impedance by admittance. It is defined as square root as under root of impedance by admittance. So there, so better if I show that equation, it will be more clear instead of saying it orally.
L by G plus J omega C.
Very good. How is that? How is that? Yes, please. Who is that? Because I can't find. Yeah.
Sir, Rashmit.
Rashmit, very good. Very good, Rashmit. What you said is right. So saying it orally, just if you see the equation, it will be more clear. So this is your characteristic equation, Z by Y. So this is R plus J omega L by this. So again, I am not going to discuss this. Just in continuation with this ZC, we need to we are going to define the surge impedance. Right. First, you are supposed to know ZC, characteristics impedance. If you know this, then you will be able to define surge impedance. So your ZC is R plus J omega L by G plus J omega C. Fine. So now what I'm doing, I'm considering a lossless line. A lossless line means the resistance is zero. Very good. Very good. R is 0, G is 0. So when R is 0, G is 0, I hope the ZC will be simplified like this, under root L by C.
L by C.
So this ZC now will denote with Z0 and we'll name it as surge impedance. Right? So surge impedance is nothing but it is a characteristics impedance if I consider for a lossless line. Right? And for this Z0, we have written Z0 in terms of L and C and in terms of Z and Y. See here, in terms of impedance and admittance and in terms of L and C, right? And in terms of open circuit impedance and short circuit impedance. And to conclude this concept, the Z0 can be defined as square root of under root Z by Y or square root of L by C or square root of open circuit impedance into short circuit impedance. Right? Last class, if you remember, we have done with that. So just if you see this slide, you will understand that. But already we did this. So this is your surge impedance. Means we are evaluating, means we are defining in terms of open circuit and short circuit, right? To define in terms of ZOC and ZSC, I said we need to represent, means we need to analyze your transmission line in terms of two-port network, right? Where the sending end voltage and sending end currents are representing or writing in terms of receiving end voltage and receiving end current. It is nothing but Vs is equal to AVR plus BIR, Is is equal to CVR plus DIR. Now what I am doing, I am finding this A and B constants. Okay, instead of finding these generalized constants, I am defining them as ZOC and ZSC. ZOC is nothing but open circuit. Open circuit is obtained when your receiving end voltage, receiving end current is zero. Means if I make my IR zero, which is nothing but open circuit. If I make VR zero, that is nothing but short circuit, because you are aware of this thing. So just we are applying that knowledge here. If you apply your knowledge here, you can see what is it. Just let me zoom this one so that we can wind up this thing. So are you able to see the screen?
Yes, sir.
So here, when IR is zero, I'll get my equations this. So if I take the ratio of Vs by Is, which is nothing but a impedance Z. So this impedance we are finding under open circuit. So that's the reason I'm writing ZOC, that's it. So ZOC is equal to Vs by Is. If I take the ratio, this VR will get cancelled. I left with AC. In the similar way, if I consider the line is short circuited, then I'll get Vs is equal to PIR, Is is equal to TIR, and take the ratio. So now when I take this ratio, this is under short circuit condition. So that's the reason what I'm doing. I'm writing ZSC. Okay, ZOC and ZSC. So if I simplify this further, IR get cancelled, you'll get with BD. So finally, ZOC is equal to A by C, ZSC is equal to B by D. Now I'm multiplying these two equations. So two terms, ZOC, ZSC. So when I do this, I'll get A by C into B by D. And from transmission line network, it is a bilateral network. So we know this, for bilateral network, the condition A is equal to D. So we'll apply that there. So when I apply that, this A and D will get cancelled. I left with B by C. So ZOC into ZSC, finally we'll get B by C. Right? Now what is this B and what is this C? Of course, they are generalized constants, but you are writing this in terms of impedances and admittances. Okay, simply directly you can write it B by C. But what is this B by C? It is product of ZOC and ZSC. But what we are doing, we are measuring your surge impedance in terms of ZOC and ZSC. So directly, if I take the ratio B by C, I can't say this is surge impedance. So what I'm supposed to do? From your characteristic equations, that is your voltage and current equations, you take out your B value and C value. You substitute here. When you substitute, you will get Z by Y. And from your previous knowledge, you know Z by Y is nothing but Z square. Because Z naught is equal to under root Z by Y. So I can write Z by Y equal to Z square. So if I put these terms aside, then I can define my surge impedance as square root of ZOC into ZSC. Right? Is that clear, please?
Yes, sir.
Is that clear? Yes. Right. So this is your search impedance. So search impedance, if you come across this word, because most often you will come across this word in stability while studying your stability subjects, studying these subjects in next semesters, coming semesters, not now. So you should have clear understanding about the search impedance. So search impedance is nothing but it is a ratio of Z square root of ZOC into ZSC, right? So now if we move on further, we'll see the importance of this. Importance means, as I said, from these three equations, one thing I can conclude is your surge impedance is independent of line length, as we discussed previously. As it is independent of line length, so it depends on the radius of the conductor and the spacing between the conductor. This is very important point. Keep it in mind. Short, medium, or long, it won't change. It varies when the radius of the conductor is changing and the distance between the conductors is changing, right? And once your transmission line is constructed or laid, we won't change them, right? So based on those values, we have calculated the typical values for your ZO. We call them as typical values. Yes, these are fixed like that. By considering your radius and distance between the conductors, they calculated this finally. So that's the reason we call it as typical values. So here, and this typical values are constant. So a single conductor, it is 400 to 600 ohms. As it varies between 400 to 600 ohms. Okay, but is a two conductor. And see this here. I have written a single conductor. Here it is bundle line. Bundle line. As what you are doing, we are bunching the strands. Your conductors are there, we'll bunch them and we'll make it as a bundle so that the cross section will reduce. When A is reducing, right? When cross section is reducing, your transfer of current will be more. So that bundle concept is bundle conductors concept. And next topic we'll discuss that in detail. Okay, just for time being, keep it in mind. For two conductor, it is Z320. Conductor is 280. For four conductor, it is 260. And for underground cables, it is 40 to 60. So most often in bits, whether it's gate or any competitive exam, they will focus on this too. For overhead transmission line, Z0 is 440, 220, like that they will mention. Similarly for underground, 40 and 60. And based on this, they'll modify the question. They'll write a question in this way. Like if Z0 is 200 ohms per phase for a 80 kilometers long line, then Z0 is dash for 100 kilometers length of the line. So here student often get confused. 80 kilometers. Now it is 100 kilometers. So Z0 is going to increase or decrease? It won't, because it is independent of line length. So it won't increase. So these are the few important conclusions regarding your surge impedance. So if you come across this word, don't get confused. Okay. This is regarding your surge impedance. Next topic is called surge impedance loading. See the word surge impedance. Where this surge impedance? We are defining this on transmission line. So don't get confused here. Most often students will get confused here. Surge impedance and surge impedance loading. We are defining surge impedance for your transmission line. Right? Now see here, surge impedance loading. Loading, where do you load? You will connect your loads at receiving end. Am I right? Jashwant. No
Yes, sir.
response.
Proceed.
Is it clear? So surge impedance
sir.
loading means now we need to consider your load point also. So far, this wave propagation, characteristic impedance, surge impedance, we have defined it for your transmission line. Now we are adding your load here. At the receiving end, we are adding the load. So there we have one more term called surge impedance loading. Right? So here I have written a definition. So before defining this, as we know, your transmission line has RLCG elements already from the day one of your what power systems. We are repeating this word more often, right? RLCNG. Okay. So as I said, we can ignore these two terms because that was due to line losses. Means R is giving the heat loss and G is providing a path for leakage currents over the insulators. So what I'm doing, I'm neglecting them. So we left with what? L and C. So L and C, as you see the characteristic behavior of L, the current always lags voltage. That is its behavior. Yes, if you see the relation between voltage and current for inductor, that always current lags voltage. Am I right? Yes, no, don't know. Yes, please.
Yes, sir. Current lags voltage in case of inductance.
What about capacitance?
Voltage
Leads.
lags, we can say in both the ways.
Yeah, we can see. Yes, what I'm writing, is that right?
Yes, sir. It's right.
So here the thing is, that is their inherent behavior. They are behaving like that. So when they are behaving like that, so here the main term to deal with is reactive power, because we call these two terms as reactive elements. Reactive element means they oppose a sudden change. Inductance will oppose sudden change in current. Capacitance will oppose sudden change in voltage. So these two reactive elements, right? So what happens? As current lags V, we can say this inductor will observe reactive power. Hope you know the reactive power symbol. I'll denote with Q. Active power with P. And what about apparent power or complex power?
Yes.
Yes, very good. So here I lags P means it is observing reactive power. That is its inherent behavior. We are not doing anything there. Similarly, if we see for capacitor, it will generate reactive power because charging current, due to charging current, it will generate your reactive power in the system. whereas inductor will absorb the reactive power.
Sir, can we change instead of generating, delivering reactive power?
Very good. That word will be very good. You can use it. Yes. Delivering. Yes. Nice. Generating. Right. Very good, Master. So it is delivering reactive power. One is observing reactive power. Right. So now the point is, when inductor is observing more reactive power, right? That is your induction machines. When they are observing more reactive power, what happens? The power factor will reduce. And power factor is reducing, the losses will increase, efficiency decreases. Right? So what I'm supposed to do? I need to compensate that loss. To compensate that loss, I'll connect a capacitor so that it will deliver that reactive power, by which your power factor improves and my losses will get reduced and efficiency improves. That's what we're doing. Just these two elements. By using these two elements, I can control my reactive power. Yes, I can increase my reactive power, or I can decrease my reactive power. Right? The reactive power in your line or any load can be varied by varying your L and C. Okay. So now my point is, before defining this surge impedance loading, you should know about this. Because if you understand this terms, observing reactive power, delivering, who is delivering reactive power, then surge impedance loading concept will be easy to understand. Right? So here, the definition is, it is defined as the load at which, see the point, at which inductive and capacitive reactive volt amperes are equal and opposite. What is saying? This QL and this QC are equal and opposite. When both are equal and opposite, one thing I can conclude. What is that? Yes. QL is compensated with QC. When QL is compensated with QC, if I check my line, the reactive element's effect is negligible. Right? When it is negligible, so I can consider my complete transmission line as a resistive network. Yes or no? That's very, very important conclusion. Let's try to understand the point here. Here, what I'm saying, inductive reactive force, that QL will be equal to QC, equal and opposite. Equal and opposite means direct compensation, and both are compensated. The total effect will be negligible. So we won't find this effects of LNC. When there is no effect of LNC, so I can say my transmission line is behaving like a resistive network. Can I say it or not?
Yes.
Yes, right? So that is what I want you to understand, right? Now, if that line is connected with a load, now I'm connecting this line with a load. At what condition? At this condition, and QL is equal to QC, and I'm connecting with a load. Then we call it as surge impedance loading. Surge impedance loading. This is your transmission line. Okay, just consider it as transmission line. This is my load. It's just I'm drawing a single line diagram. Okay, this is my load L, right? If it is loaded and it is acting as a completely pure resistive network, then that is called surge impedance loading or natural loading of the line. Please try to understand the point here. Surge impedance is on line, loading is at receiving end, right? So when this condition is there, so practically we can't define this, just to analyze the
Sir,
for
here we
analysis
can
purpose.
say that surge impedance is
Yes, please.
equal to resistance.
Yes, please.
Sir, can we say that surge impedance is equal to the resistance of that line?
అంతే కదా, it is behaving like complete resistive network, resistance కదా.
Yes, sir.
At this condition, please do keep this point in mind. When QL is equal to QC, equal and opposite compensation is happening, then at that time you are supposed to term that as surge impedance loading. Generally surge impedance is under root Z by Y. Okay, don't get
Yes, sir.
confused that and this one. Is it clear,
So
Mr.?
we can say that power delivered to the load when the resistance of that network is equal to surge impedance.
That's it. Right? So this is the definition of surge impedance loading. Now I will write the equation, surge impedance loading equation. So I've written the equation also. So here you can see this. The power transmitted under that condition is given by V square RL by Z naught. So this RL is at receiving end. The load at receiving end, RL, is the load connected at receiving end. The voltage is called VRL. This we are naming it as VRL. Okay. So now we'll see this, how we got this VRL square. Okay. Right. Now say this. Let V is the phase voltage at the receiving end, I phase current, L series inductance per phase, XL series inductive reactance, XC shunt capacitor reactance. So these terms, you know this already. You are been studying these terms in day one of transmission. Z naught is a new term, surge impedance per phase. Now from this I can write this. Capacitive VARs, that is nothing but your QC. Nothing but your QC, I can write it as V square by XC. So further I can write it as V square into omega C. As in terms of capacitive reactance or in terms of direct capacitance, we can use any equation. So V square omega C or V square by XC. In the similar way, inductive volt amperes, nothing but your QL. Nothing but your QL. QL is equal to I square XL. Right. So I square XL or I square omega. Same as previous one. We are writing in terms of inductive reactance or direct in terms of inductance. Now what is my condition? My condition is
QL equal to QC.
I need to equate them. So now I'm equating them. V square omega C equal to I square omega C. So when I equate them, surge impedance, right? That's a very simple equation, just we are equating them. Okay. So next, oh wait, let me erase this again. So here you may get it out. Sir, already we know Z naught is under root L by C. We have a formula already. So again, same thing you are getting. Yes, same thing you are getting. Here we got under root L by C in this case by equating QC and QL. Whereas in previous case, what we did? We
For a
made,
lossless line.
means we have considered lossless transmission line. So please don't get confused there. Okay. అంటే స్టూడెంట్స్ మే థింక్ అరే ఈ జెడ్ నాట్ ఇక్కడ కూడా రూట్ ఎల్ బై సి వచ్చింది, అక్కడ కూడా సేమ్ వచ్చింది. ఆ కాన్సెప్ట్ వేరు, ఈ కాన్సెప్ట్ వేరు. ఓకే, ద ఫార్ములా ఇస్ సేమ్, formula is same, but the concept is different here. Okay, so this is your Z naught. Now if you move on further, so as I said just now one statement, it is acting as purely resistor network. Just for understanding purpose, I written this. You can see this. At this load, voltage and current are in phase at all the points, because direct compensation is being done with your QL and QC. Both are getting cancelled out. So my voltage and current will be in phase at all points throughout the entire length of the line. Right? Now what I'm doing, under such conditions, now I am connecting means a load. The line is terminated in its surge impedance Z naught, which is purely resistive. Just now what I explained it, just the statements are there. Okay, nothing new on this. Next. This is how you got your VRL spell Z naught. So now here for single phase and three phase I'm showing. It's same thing here. So single phase, your surge impedance power equation is VI cos phi. So here P resembles per phase, I is also per phase. So VI cos phi. This is for single phase. So now as the load is purely resistive, so what is the power factor will be unity. So I left with PR equal to VP into IP. Right? So now from your previous equation, V by I equal to Z naught. From that I can write I equal to V by P. So from there, if I simplify it, I'll get PR equal to VP square by Z naught. So this is a power transmitted under surge impedance loading. Right? Surge impedance loading. The power transmitted is given by V square by Z naught, the single phase. Now, if I want to write in terms of line voltage, what I'm supposed to do? Just you write VP equal to VL by root 3. So VL by root 3 will be VL square by 3. So which is nothing but 1 by 3 times line voltage square by Z naught. So I haven't mentioned here. Just directly it is understood. Just we need to replace VP with VL. VL by root 3. Done. So next, similar for three phase, three conductors are there. So power will be 3 times. So directly 3 times of PR. So directly here VP square by Z naught. So if I write in terms of L, I need to divide it by 3. That 3, this 3 will get cancelled. You're left with VL square by Z naught. Same equation. Now, so just we have seen this how we got this thing. Okay, so here the receiving end voltage is in kV, kilovolts, right? Not in volts. Okay, kilovolts square. What happens? kV square 1000 into 1000 megawatts. So that's the reason we are writing as megawatts. Okay, is that clear? This is your power transmitted under surge impedance loading. Now we'll see the importance of this. So if you see the importance, by seeing the equation, I think you can draw some conclusions from seeing this equation. What is this? That is nothing but power transmission, which is equal to VRL square by Z naught. Okay, so always as a consumer point of view, we expect more power. More power means not beyond rated power. Just I'm saying because all the loads are connected in parallel, so this power transmission should satisfy all those loads. So in that sense, I'm saying we expect more power, not like overrating. Okay, don't get confused. So to have more power transmission, means power transmission, to increase this power transmission, simply I can increase voltage or I can decrease my surge impedance, right? I can increase my voltage or I can decrease my surge impedance. So when you are increasing voltage, there will be limitation, right? Hence, what I want to conclude is to have more power transmission, we can increase the voltage or we can decrease the surge impedance, right? So when you are increasing the voltage, till what extent you will increase? And we need to consider economical factor also, right? Well, just to increase the voltage, you need to design the conductors to handle that much of higher voltages, right? So there what happens when I go over more higher voltages in lines, your costs will be affected. So it has some optimum point. In the similar way, Z naught. What is Z naught? Z naught is nothing but your L by C. Please be attentive everyone. From this we are making important conclusion. Z naught is nothing but under root L by C. Okay. So to decrease my Z naught, I'm supposed to increase my capacitance, or else I'm supposed to decrease my inductance. Either I should decrease the inductance to decrease impedance Z naught, or I should increase the capacitance to decrease the Z naught. Means as a consequence, there will be more power transfer to achieve that maximum power transfer, right? So this is the thing, means either decreasing L or increasing C. So this decreasing L or increasing C we call technically as compensation. Call them as compensation. If I decrease C, so increase C, reactive compensation means I'm increasing the reactive volt amperes. Decreasing elements, I'm reducing reactive volt amperes. So this is how this compensation will happen. We have the topic. Next concept is that, okay, there we'll see in detail. So just for time being, we can draw two conclusions. One is to have a maximum power transfer. Either I'm supposed to increase the voltage or I'm supposed to decrease the surge impedance loading. Z naught. Fine. So what are the points here? We have just I explained those points. Okay. So I am not reading out those points again because I explained it. Next, but I think I'll miss this point. EHV lines, extra high voltage lines, we have a relation. Power transfer will be given as K times PR. Already you know PR equal to VRL square by Z naught. Now this factor K, This K is 0.85 for long transmission line, and this is 1.3 for short transmission lines. Because I said there should be some optimum point, because simply I can't go for simply increasing voltages, right? So this is the relation we need to follow. P equal to K into PR. This K is 0.85 for long lines, and it is 1.3 for short lines. Hope you are following. Yes, no, don't know.
Yes, sir.
Yes.
Very good.
Yes, sir.
Very good. Thanks for your response. Next. This is very, very important. From this column, see, I'm drawing star also. Okay. Just to keep understand, this is very important here. See here. I'm taking first condition, right? When surge impedance loading, that's what are the load you are connecting at receiving end. When your surge impedance loading is greater than that load, then your receiving end voltage will be greater than sending end voltage. Yes, please. Noise. Then the receiving end voltage will be greater than sending end voltage. We can say the reactive volt amperes are being generated or delivered more than required, and we call this phenomena as Ferranti effect. So how this Ferranti effect is happening, next class I'll show by showing that phasors, by drawing the phasors. Okay, so just for time being, keep it in mind. It gives an effect called Ferranti effect, where receiving voltage is greater than sending end voltage. Now another condition, if load is greater than SIL, that is surge impedance loading, then it is your normal operation. Receiving end voltage will be less than sending end voltage. So when this is happening, it means most of the power is occurring or taking place as loss. So what I'm supposed to do? To compensate that loss, I need to use some compensation techniques. Right? That is nothing but series or shunt compensation I'm supposed to do. Okay. Now what is happening? When load is greater than SIL, then it is observing more reactive power. When it is observing more reactive power, as I said previously, power factor decreases, losses increases, efficiency decreases. So to overcome that, I need to apply some compensation techniques. The third one, and load is equal to surge impedance loading. That is nothing but VAR is equal to VS. That is your ideal case. Practically, it won't happen, but there is a chance this thing, Ferranti effect. You can notice that Ferranti effect in power systems lab. You have an experiment. There you can note receiving end voltage will be greater than sending end voltage. That is due to your capacitance effect. Was already we know, and transmission line, the capacitance, due to that capacitance effect, there will be charging current even though the transmission line is open circuited. And if transmission line is open circuited, we know one point, that is receiving end current will be zero. But what about capacitance current? For capacitance, you need just parallel conductors, so charging current will be there. So that is one of the drawback. Drawback means simply just if you are disconnecting the line and if you are touching the conductor, you may get shocked, because the charging current, we are providing a path for that. Okay, so whenever any fault occurs, the linemans, what they will do, they'll disconnect it and they'll connect that insulator with the ground, so that and then later they will resolve the problem and then reconnect the circuit. The steps they will follow. Fine. So this is your surge impedance loading, Nana. With this, you're done with your surge impedance loading. Right? Any doubts so far? If you have any doubts, please ask me. And I already know you have 3 options. You can ask right now. You can WhatsApp me your doubt, or you can call me. Option is yours. Because today I want to stop. Why this topic? Because next we need to see that. What is it? Tuned power lines. So tomorrow morning we'll see that tune. Tomorrow morning I have class 11 o'clock. So we'll see that surge impedance loading. Sorry, tuned power lines concept. Because it will take half an hour to 40 minutes again. So we have only 2-3 minutes. So I want to terminate the session. Those who have doubts, please ask your
Sir, do we have the equivalent circuit representation of a long line?
attendance in chat box, and you may leave. You can leave.